Hello everyone. Welcome back to the Heterogeneous Parallel Programming class. This is lecture 1.3 Portability and Scalability in Heterogeneous Parallel Computing. The objective of this lecture is to help you to understand the importance and nature of scalability and portability in parallel programming. This slide shows that data that was published by IBM in 2010. And this graph shows that the hardware costs and software costs have been both growing exponentially over the years. And this is a log plot, so a linear curve in this plot is an exponential curve. And the software cost is measured by lines per chip, and it has been growing by 2 times every 10 months. And the hardware cost is measured by gates per chip, and this is has been increasing by 2 times every 18 months. Therefore, the software cost has been growing much faster than the hardware cost. So even though the software cost started to be lower than hardware, but at this point, after 2010, the software cost has essentially exceeded the hardware cost. And it has been growing faster. So the software cost is going to be much, much more than hardware cost in the years to come. So in the future, all the systems need to be able to minimize software development cost or redevelopment cost. And this leads to the consideration of scalability and portability. The first aspect of software cost control is scalability. If we develop an application to run well on Core A, what we'd like to do is we'd like to make sure that the same application without significant redevelopment can run efficiently on the next version of Core A, let's say Core A 2.0. So this allows us to use the same application when a new generation of hardware is introduced. And whenever scalability holds, then the developer does not need to revise the software in order to run well on a new generation of software, therefore reducing the redevelopment cost. There's another dimension of scalability. Whenever an application runs well on one Core A, we will also like it to run well on multiples of these Core A's or more of the same cores. And this allows us to add performance by adding more hardware into the system. In many situations, the vendors would like to introduce multiple versions of hardware, and each version will have increasingly more amount of hardware available to the users. So if we can develop a piece of software that is scalable to run well on more of the same cores, then this gives the vendor the scalability of their hardware, so that when they introduce more hardware, the users can actually observe increased performance from the application. In the future, we expect that there will be several generations of hardware where performance will be increased by adjusting many of these parameters. For example, the number of compute units or the number of cores, and the number of threads, the increasing vector length, the increased pipeline depth, and increased DRAM burst size, increased the number of DRAM channels, and increasing data movement latency. All these hardware parameters can significantly affect the performance of the application, and oftentimes applications need to be able to be tuned to some settings of these parameters. So, but the programming style that we use in this course address these needs by supporting fine-grained problem decomposition and dynamic thread scheduling, so that the application that you write according to this programming style will be able to automatically adjust to a fairly wide range of parameter values that the hardware vendors may change. So this allows your application to run well on one generation of hardware and continue to run well on a future generation of hardware. And also, if your application runs well on one of the cores, you can expect the application to also run well on more of the same cores. The second dimension of software cost control is portability. Portability is defined as if we develop an application to run well on core A, we would also like it to be able to run well on different types of cores. In this case, core B and core C in the picture. So oftentimes, the application developed for core A may be initially running on one vendor product. And but if the application is portable, then the users can expect to run the same application on different hardware types, oftentimes from different hardware vendors, to also run well. So this can also decrease the software cost because the developer will not need to redevelop or revise the application so that the application can run well on other types of vendor systems. And a lot of times we will see different design styles from different vendors. For GPUs, oftentimes we will see very significant design styles as illustrated in this picture. And in terms of the particular kinds of differences, we can expect to see that for the CPU cores, we would see different instruction set architectures, such as x86 versus ARM versus other types of instruction set architectures. And these instruction set architectures oftentimes would require different compiler code generation and so on. So and that oftentimes will affect the portability of your application. And we also have different design styles, even based on the same instruction set architecture. We could have latency-oriented CPU designs versus throughput-oriented GPU designs. And so when we develop a piece of code, can we expect to run? Can we expect it to run well on a latency-oriented CPU if it runs well on a throughput-oriented GPU? And the third kind of dimension of portability often comes with different styles of parallelism in the processor core. There's a design style called VRW, and there's a design style SIMD, and there's a design style of multi-threading. So we're going to actually touch quite a bit of that this level of differences for hardware. And then it also will come to how we organize DRAMs in the system, whether it's a shared memory model or distributed memory model. So all these dimensions will affect the portability of your application. So when we work towards the end of the course, we will have we'll introduce emerging standards such as OpenCL and heterogeneous system architecture that will help to address the portability of your applications. So at this point, we have completed all the high-level introduction and context information lectures. So starting from next lecture, we're going to be introducing the CUDA programming interface and begin to help you to develop your lab application assignments. So for those of you who would like to learn more about the topic and the context information, I would like to encourage you to read Chapter 1 of the textbook. Thank you.